So this video is going to go over what we call atomic mass. Atomic mass is what we call a weighted average. So for these notes, you might want to use a highlighter just to highlight a couple of the terms. So a weighted average is different than a typical average because you are, if you have a typical average, you take all of the masses that you are taking and you divide by however many you have. In a weighted average, you're looking at how much of each one of the isotope is contributing to the overall. So we're going to be using something called AMU, atomic mass unit. And this is based off of what we call carbon-12, that particular isotope. The reason we are picking on carbon-12 is we are carbon-based life forms, and carbon-12 is about 98, almost 99% of all of the carbon that we have existing in our planet. So we are taking essentially 1/12 of the mass and calling it an AMU. So in nature, we have a mixture of two or more isotopes. Okay, so we have a mixture of two or more isotopes. So because of that, we have to essentially take a weighted average. So everything's based off of carbon. Everything's based off of carbon. And if you go to the penny isotope lab, it will give you some instances there. So in order to calculate atomic mass, you need 3 bits of information. You need to know how many isotopes you have. You need to know the mass of each isotope, and this is going to be in AMUs. Okay, AMUs. And then finally, you need to know the percentage, or what we call the natural abundance of each one of those isotopes. So I'm going to work an example or two just so you can get the feel of this, but the penny isotope lab should help you with this as well. So I have 2 isotopes of chlorine, chlorine-35 and chlorine-37. Okay, so writing isotope notation for both of these. Chlorine-35, about 75.77% of it is chlorine-35, and 24.23% is chlorine-37. The mass of each one of these isotopes is in AMU. So this is 34.969 AMUs, and it depends upon your source of how many digits this goes out. 36.966 AMUs, I believe, if I could read my handwriting. So this is where the sig figs are coming from. They are not coming from the percentages. They're always going to come from the AMU. So since I have 3 digits after the decimal, I'm going to do 3 digits after the decimal for my final answer. And again, it's not a hard, fast rule. It's just going to be how, if everybody does it the same, then we're all on the same page. So I'm going to take the percentages and divide them by 100 to get them to a decimal. So I'm going to take 0.7577 and multiply it by 34.969 AMUs. And then I'm going to add it to the 24.23. So I'm going to move the decimal over, and I'm going to have it multiplied by 36.966 AMUs. So when you multiply and then add together, you get about 35.453. That is generally what you're going to get. And if you have a periodic table, which I am trying to find mine. I have my periodic table now. There you go, Miss Brucker. Is if you look it up, the atomic mass or atomic weight is what you will see on your web periodic table. You will see it's around 35.45. This is about 35.453, depending upon how many digits you take it out. So this is what you call your atomic mass, okay? So when you look at the periodic table, you would have 35.453 as that bottom number, So this is what we call the atomic mass or the atomic weight of the element, okay? This is not the same as mass number, okay? Do not mix these two together. So atomic mass is the average mass of all the isotopes, okay? All the isotopes of chlorine. I have 2 of them, so I massed them all together and took the weighted average. The mass number is just the number of protons and neutrons in the nucleus. That's all it is. Atomic mass is going to be a decimal when you do the calculation. Atomic mass is going to be the decimal, while mass number is going to be a whole number. Okay, so again, a way for you to distinguish between the two. Atomic mass is found on the periodic table. Okay, it's found on the periodic table. The mass number is not on the periodic table. I have to get this from, again, I needed the 35, I needed the 37 in order to figure out how many neutrons I have. I have to get it from the isotope notation in order for me to know what the mass number is. That has to be given to me in a problem, one way or the other, either giving me the neutrons or you're giving me that. So if you go to the next page of my notes, I found this pretty simple list of some common elements and their corresponding symbols and their corresponding natural abundances. And so you could see again, chlorine on the bottom has 35 and 37. And so these were the numbers I was using in that problem. And that's where I got my overall atomic mass. So if I look at something like sulfur, again, we use sulfur when we did the mole. Okay, we look it up and it's 32.06. Well, that's coming from the fact that you have 4 naturally occurring isotopes, okay? And they have their own percentage, their own natural abundance. And so in order to figure out this 32.06, you're going to change the 95 into a decimal and multiply it by this number. And you're going to do the same thing for each one of these and add it together. Okay, so you could kind of prove it to yourself by doing these calculations. So I'm going to do one more with you, so you could kind of see how this works. And then you're going to have plenty of practice when we do the penny isotope lab. So we're going to do potassium. Potassium has 3 natural occurring isotopes: potassium 39, potassium 40, and potassium 41. Okay, all having 19. So I know that they're isotopes because their bottom numbers are the same, but their mass numbers are different. Okay, so this is KKK. Every time I do this example, I'm like, oh, KKK. So potassium 39 is about 93.258%. Potassium 40 is about 0.0117%. And then the last one, potassium 41, is about 6.730%. Their individual masses are 38.963 AMU, 39.964 AMU, and then 40.962 AMU. So again, all of this information has to be provided to you in order for you to do the problem, okay? So I apologize for my awful handwriting. So see if you could pause the video. Okay, I'm going to pause the video as well, and then I'm going to show you the answer so you could see how you did. So we have the final answer is about 39.099 AMUs. And again, we're going to make up some data because, again, you could have just looked on your periodic table in order for you to figure out that number. So sometimes you're going to see that we've made up elements so that we don't have anybody just kind of writing down a number. I like this one because 0.0117, you have to move the decimal 2 over. So that's 0.000117. It's, again, a natural occurrence, essentially, is for you guys just to move that decimal in front of the number. But when you see a decimal like this, you have to remember you still have to divide it by 100. You still have to divide it. And this one comes out to be 0.0673. So that is how you do atomic mass. And that is how we got it from the periodic table. And everything is based off of, again, carbon 12. That is our standard. So again, with all of these things, we always start with a standard and then we work from there.